Good evening, class. Today is the last section of Chapter 6. It's arguably the toughest section, and I think so myself. What we're trying to do here is we're trying to give you 4 different ways to set up proportions, and these all deal with parallel lines. So if you're looking for parallel lines and you're looking for proportions, it's probably one of these theorems. The first one that we're going to look at is triangle proportionality theorem. Yep. It's called the triangle proportionality theorem. Kind of important. If a line parallel to one side of a triangle intersects the other 2 sides, then it divides the 2 sides proportionally. So if I look at this picture here, these 2 parallel lines, in fact it's this one they're talking about. If a line parallel to one side of a triangle intersects the other 2 sides. So they're talking about segment BD over here. It intersects both sides and is parallel to the 3rd side here. It divides the sides proportionally. What that means is segment AB to segment BC has to be the same ratio as segment ED to segment CD, as shown right here. This has to be true in this situation. If you know how to set up the proportion, it's pretty straightforward from there. If you don't, this becomes really tough. So, let's try and do a few examples of this, setting up the proportion. Example 1. Find the length of segment AB. Alright, so if I think about the theorem I just discussed, or just said, I said that if I have a segment here that's parallel to this side, and it goes through both sides. It does. It divides the sides proportionally. So that means this part here, x to 12, has to be the same ratio as 13.5 to 10. See how I went x to 12, 13.5 to 10, I went from the same part. So between the parallel lines to outside the parallel lines equals between the parallel lines to outside the parallel lines. At this point, if I'm solving for the length of segment AB, I just cross multiply and solve. So 10x equals 162. So x is 16.2. However, I was looking for length of segment AB, so I'm going to report my answer that way. Alright, try and set up the proportion on the right side. If you did this correctly, I'm going to choose a different variable, let's say y. It's going to be y to 16, dividing the side evenly, and it should be equal to 25 to 25. Okay, now that I've set up this proportion, I'm pretty sure I know what y is. It's probably 16. But just to be sure, let's cross multiply. 25y equals 400. Divide both sides by 25, I get 16. And I'm like, no way! Didn't see that one coming. However, once set up the proportion, it was pretty straightforward what it is. So length of segment AB equals 16. Alright, there we go. These are examples of how to set up the proportion. Let's look at one slightly tougher. Find the variable, find the value of each variable. And I don't just give you 1, I just don't give you 2, I give you 3. Alright, if I look at this one here, what I notice right away is that I have multiple parallel lines. But it still is true that each line divides it proportionally. If I look here, this part to this part should equal this part to this part. Because I'm ignoring this entire AGEF part of the triangle. That's all gone. So I'm only looking from AE inward. So x to 12 equals 13.5 to 10. I feel like I've just done this. 10x equals 162. X is 16.2. Alright, so I know x, I'm going to plug it in. 16.2. Now I'm trying to find z here. If I compare z, I'm essentially going to pretend as if this doesn't exist here temporarily. So when I look at this, it now becomes one of those, oh, it's this part to this part. So z to 23.5. Because that's 10 plus 13.5, should equal 24 to 16.2 plus 12, or 28.2. Now that I have my proportion set up, I'm going to redraw the part I erased. And now I'm just going to solve my proportion. 28.2z equals, well, 23.5 times 24, or better known as 564. Divide both sides by 28.2, and somehow I get a nice little number, 20. I'm trying to find y. It's part of my big triangle here as y. And if I look at the full side length for one of the sides, I get 52.2. For the other one, I get 43.5. And the only other triangle I really have to compare it to is a small one here, BCD, which I know is 12, 10, and 14. I know that this one and this one end up being parallel. And if I do a little bit of work here, I could tell you that this angle and this angle are congruent. This angle here and this angle here are congruent. So I know that these two triangles here have to be congruent by angle-angle similarity postulate. So now all I have to do is set up the correct proportion. The hard part here was looking at this as a triangle and looking at the big thing as a triangle. And now that I have two similar triangles, I just set up the correct proportion. So if I look at sides, I can do 14 to y, and that would equal 10 to 43.5. Cross multiply, 10y equals, well, I don't know what 14 times 43.5 off the top of my head is. But I do know, after I put it in a calculator, it's 609. Divide both sides by 10, I get 60.9, and I found my last variable. So, it's just applying this rule over and over and over again until I finally get everything I need. Alright, the next theorem that we talk about is the converse of the triangle proportionality theorem. It's if I have my sides divided proportionally, then I know it is parallel to the third side. So, what this theorem says is if I know this to be true, length of segment AB to length of segment BC equals length of segment ED to length of segment DC, then, so if this is true, then I know without a shadow of a doubt that segment BD is parallel to segment AE. So, if the sides are divided proportionally, then the two parts have to be parallel. The line and the third side. Alright. So this one, basically what I'll be having you use this for is tell me if you can determine if the two lines are parallel. And it's going to be pretty straightforward. Is this proportion true? If yes, parallel. If not, not parallel. So, determine whether you can tell me for sure, with 100% certainty, that length of segment BE is parallel to segment CD. Well, let's set up the proportion. If the proportion is true, then I know that the lines have to be parallel. So in this case, this is what I know to be true. So I'm going to compare this side, 10 to 12, and I'm going to compare it to 14 to 16.5. If parallel, those are true. If not parallel, it's false. So cross multiply, I get 165 equals, I get 168. And I noticed that I made a mistake. This I copied down wrong. It's supposed to be 16.8, 16.8. So when I cross multiply, I was supposed to get 168. My bad. It is true. Therefore, segment BE has to be parallel to segment CD. No way around it. Because the sides are divided proportionally. So I would say converse to the triangle proportionality theorem. And there I go. I have stated that they are parallel, and I have explained why I know it. It's the converse of the triangle proportionality theorem. Alright, so either A, you're looking for variables because you know the lines are parallel, or B, you're trying to tell me the lines are parallel. Alright, the next theorem is a little bit tougher / easier at the same time. If I know 3 lines are parallel, then what I also know is that they have the lines being divided proportionally. So, for instance, I know that these 3 lines here are parallel. I then know that these 2 transversals have to be divided proportionally. What that means, if I compare this length to this length, AB to BC, it has to be the same ratio as this length to this length. So length of segment DE to length of segment EF. That's all this theorem says, is if I have this setup, 3 or more parallel lines divided by 2 transversals, it divides the transversals proportionally. So AB to BC equals DE to EF. Awesome. Let's apply this. I want you to find the values of X, Y, and Z, and I give you a picture that has 3 or more parallel lines. In fact, it has 4. Alright, so I look. If I pretended that this part wasn't here, I could then say Y to 21 has to have the same ratio as 20 to 25. I've done the hard part. I set up the proportion. At this point, you just cross multiply and you solve. So 25y equals 420. Y equals, I want to say it's 16.4, 16.8. Try and set up the proportion for x. Well, if I know this is 16.8, what I'm going to do mentally is I'm going to discard this entire right side. So now that I know this is 16.8, I can compare x to 16.8, and I'm going to do 15 to 20. Awesome. Cross multiply. 20x equals 252. Divide both sides by 20. Divide both sides by 20, and I get 12.6 to be x. So, if you got a different proportion, but you solved it and you got this part, you set up a correct proportion. It's just you set it up differently than me, which it's fine. Just make sure that you get this right answer. So there I go. Setting up the proportions is the tough part. I chose y to 21 equals 20 to 25. It happens that if I would change the means here, I noticed that I could say y to 20 equals 21 to 25. That is another way you could set up this proportion. So I could have done x to 15 equals 21 to 25. It's going to be true. Just the way it works. Alright, the last theorem is a neat one. It says, if a ray bisects an angle of a triangle, then it divides the opposite sides into segments whose lengths are proportional to the lengths of the other 2 sides. It sounds real complicated, but it's not that bad. What it's saying is if I would have a triangle like this, and I have a ray that bisects the angle over here, what I know to be true would be that the side, it's segments. So in this case, AD to DC. So this length to this length. It's going to be the same proportion, or it's going to be the same ratio or proportional to the lengths of the other 2 sides. So AB to BC. Now, why did I choose AB to BC and I didn't do BC to AB? Well, I started with AD, so I start with AB on top. It has to be the same ratio, so it means it matches up correspondingly. This ratio has to be true if this is an angle bisector. Always. AD to DC has to equal AB to BC. If you can understand how to set up this ratio whenever you see an angle bisector, you've got it good, because at that point, all you have to do is cross, multiply, and solve. So, this is how we set up the proportion. Let's try and attempt this in 2 different problems. One that looks just like this, but we're going to use numbers. And another one that's slightly different. Try and set up these 2 ratios. proportions. If you can do that, you're probably going to get this right. Alright, so let's take a look. I take a look at the side that's being divided by the bisector. The side being divided by the bisector. I'm going to compare 9 to x. Now I also look, that means I compare, because I started with 9, I'm going to start with 16 to 12. Boom, that's my proportion. If you have an inverse, or if you have these numbers switched around, or a similar form, you still have it right, you just set up differently than mine. Cross multiply. 16x equals 108. Divide both sides by 16, you should get 6.75. Awesome. This one over here. Set up the proportion. Well, I'm going to do y to 16. Y to 16. So I started with y, so I'm going to have to match it up to 21 to 32. Now that I have my proportion, it's just as simple as cross multiply and solve. 32y equals 336. Divide both sides by 32, and you should get 10.5. So the hard part here is setting up the correct proportion. Then you cross multiply and solve. If you have questions about how to set up this proportion, ask me. But the book does a pretty good job at laying it out. The last example is just a tougher example of what I did here. Alright, so I look at this. Well, the first part that I'm probably actually going to do here is I'm probably going to try and find z. That'll be the first part I do. Alright, so to do that, I'm going to do 9 to z equals 12 to 9. So 9 to z equals 12 to 9. I basically ignored this entire part where my hand is. And once I have my proportion set up, I just cross multiply. 81 equals 12z. Divide both sides by 12. I get 6.75. Once I find that, let's put 6.75 here. Alright, I realize that it makes this side a little bit difficult to do if you don't have this here. So I'm going to give you y. It's 15.75. Okay? Now, if I'm trying to look for this side, I have to be able to set up a ratio of 2 corresponding side lengths of 2 similar triangles. I don't know if these lines are parallel. However, I do know that this is an angle bisector. So I know that 21 to 15.75 has to equal, well, the full length here. 21 to 15.75, and then the full length, 28 to 9 plus x. And now that I've used my rule again, the side being split up is the same ratio as side to side. And it's the full length of the side in this case because I'm using the full big one. So at this point, I cross multiply and I solve. 441 is 15.75 times 28. 21 times 9 is 189. And 21 times x is 21x. I really guess I should put it like this first. 21 times 9 plus x, and then distribute it to both parts. So that's when I get the 189 plus 21x equals 441. Subtract 189 from both sides. 252. And then you divide both sides by 21, and you get x to be 12. Alright, so we found 2 variables. If you need help with y, see me. However, there we go. We've used all of our resources to figure out this information, and I think we're good to go. So, if I give you an example like this, just apply this rule over and over again. You should be able to get most, if not all, of it. So there's 4 new theorems, and these theorems will help you set up a correct proportion. It's just knowing which proportion to use when. If it's parallel lines, you're going to use either the transversal one, or you're going to use the triangle proportionality theorem. If it's an angle bisector, you're using this one here. Well, that's all I have for you today. Till next time.